Hello, today I'm going to model some examples of dynamic objects we have in computer control systems and explain how to compare the differential equation of each object to the responsive transfer function. First dynamic object I want to present is proportional controller. One of the most important applications of proportional controller, fixed bias or offset, is the zero load process. It means the dynamic characteristic of process doesn't get any disturbance even as flow doesn't get through the controller for small duration. In a proportional system, the output is just proportional to the input, with k being just a constant. After applying the Laplace transform on both sides, we change yt to the ys and ut to the us to finally get the transfer function equals k. The differentiator is substantially a high-pass filter. It can generate a square wave with produce alternating directions voltage spikes when a square wave is applied. In an ideal cases, a differentiator will reverse the effect of an integrator on a waveform, and vice versa. Hence, they are most commonly used in wave shaping circuits to detect high-frequency components in an input signal. Differentiators are an important part of electronic analog computers and analog PID controllers. They are also used in FM modulators as rate of change detectors. In this case, the output is proportional to the derivative of the input. Applying Laplace transform on first derivative of u gives us us times s, and then yields to the transfer function k times s. The next one is integrator. Talking about the applications of integrator, we have to mention about OP-AMP. Integrating amplifiers are used to perform calculus operations in analog computers. Integrating circuits are most commonly used in analog to digit converters, ramp generators, and also in wave shaping applications. Now the output is proportional to the integral of the input. The integral after using Laplace transform equals to 1 over s. Therefore, the transfer function equals k over s. First-order systems are also called first-order lags, exponential lags, or exponential stages. First-order systems are massless systems, which means that they do not exhibit the property of inertia of the first order. A good example of a first-order system is thermometer. If a thermometer is initially at the temperature of 0 Fahrenheit and is suddenly thrust at time equals to into a constant temperature water bath held at a temperature of 100 Fahrenheit, it will immediately begin to flow into the thermometer, and the temperature of the thermometer will begin to rise. On the basis of the previous example, we can easily calculate the transfer function of the dynamic object is b1 over s plus a1. A system can be built with an inherent delay. Delays are units that cause a time shift in the input signal, but that don't affect the signal characteristics. An ideal delay is a delay system that doesn't affect the signal characteristic at all, and that delay that signal for an exact amount of time. Some delays, like processing delays or transmission delays, are unintentional. Other delays, however, such as synchronization delays, are an integral part of the system. In this case, the output at time t is proportional to the input evaluated at previous time, t minus t0. Therefore, the output is delayed from the input. After applying Laplace transform on ut minus t0, we get e to the power of st0 times us. The transfer function result is e to the power of st0. Oscillator produces a periodic oscillation electronic signal, often a sine wave or a square wave. Common examples of signal generated by oscillators include signal broadcast by radio and television transmitters, clock signals that regulate computers and quartz clocks, and the sound produced by electronic beepers and video games. At the end, we have the general differential equation for oscillatory systems. The transfer function of those is b2 over s to the power of 2 plus sa1 plus a2. That's all for today. Thank you for watching.